Alright, Year 12, welcome back. Today in this session we'll cover how to determine the area of under the curve, so from the curve to the x-axis, and at the same time I'll continue to 11i, which is the area between two curves as the methods are the same. So let's continue. Alright. So just a little bit of a reminder. So here, when you have a function that is greater than 0 over the interval from a to b, when you anti-differentiate that function over that interval, the integral is positive, which is the same as your area. Also, the way usually they ask you the question is the area under the curve, so it's from the red curve to between the x-axis and also the vertical line x equal a and x equal b. Some of the questions might specify the vertical line in that equation form, so just be mindful of the way the question is worded. If the function is under the curve, so again you will still have some similarity with the x-axis, the vertical line x equals a and x equals b. When you calculate the integral, so just ignore for a second the negative sign outside, the integral of that function over that interval is going to be negative. So now we're going to multiply by -1, so we get a positive value, which is going to be your area. This will be more the general situation. Your function is crossing the x-axis, so a section of it will be above the x-axis, another section will be below. So that c-value will be, which will be an element of that interval, so it can't be the boundary. F of c equals 0 indicates that it is an x-intercept, which is important as sometime in some of the questions you will not be given the c value, so you will have to solve that equation for c. In the section where the function is positive over there, then the function is negative from a to c, then what we can do is to determine the area. The positive section from c to b is that integral, and from a to c you will take the opposite. So annotated here, when you want to determine the area under the curve, the sign of the function f of x in the given interval is a critical factor. It is very important that you analyze the sign function and adapt with keeping the positive or take the negative if the function is below the curve. As an example here, is asking you, so you sketch this function, which is a quadratic. It's already in a turning point form. 0 to 2 is your turning point. The function is above the x-axis. You need to determine the area from x equals 0 to x equals 1. So x equals 0 is your y-axis, x equals 1 will be about here. You set your antiderivative, which is going to be your area, and you use your algebraic method to determine the area, and again eventually you simplify to a positive value. Don't forget to specify that the area is in square units, as usually in calculus they don't specify any distance unit to let's say those values x equals 0 to 1. There's no indicate, it doesn't indicate it's in millimeters, centimeters or meters. Here is the general situation. Refer to exercise 11f, which is your question 8. Here is your integral. It gives you a graph and you need to determine in part B the area. The first part is your integral, so have a go, pause the video and try to answer both parts. Alright, so here I'm just going to focus on part B. So part A, you're just going to have to anti-differentiate and just use the -1 and 4 as your respective boundaries. For the area, you can see you have two intercepts, 0 and 3. So you will split your integral from -1 to 0, 0 to 3, 3 to 4, and for the portions where the function is below the curve, so from -1 to 0 you will have a negative, from 3 to 4 you will have a negative as well. So as you evaluate all of that, that will give you your area. Okay, I'm just don't like the way the notation here. So the right hand side is your area, your left hand side is actually your integral, so they're not gonna be necessarily equal. This part will answer part A, and here when you will do the evaluate the right hand side, that will be your exact area. Also, the exact part of it indicate your, if you have a fractional form or surds, always leave your answer in simplified form. Do not round it off or estimate into a decimal form until the question specifies it. Alright, with the application of that, you should be able to find the area between two curves. Not really more difficult, and let's go straight to the concept. When you have, so you have two curves, F and G. Here we look at a simple example. We want to find the area from A to B, but F is in red is above G, meaning that F is always greater than G. When you want to find the area between the curves, find the area of the function F, find the area of the function G to the x-axis or under the curve, do the subtraction, and I will give you the area in between. For you, in terms of calculus, what you do is you rewrite this as the integral from the same interval of a new function that will be the difference between F and G. And then you will do use your method of your antiderivative to calculate the answer. So here was an example. In the general solution, which is, I'll talk about it later. Let's do an example first with this situation. So here you have two functions. That's your F, that's your G. Over this interval, the function F is always greater than G. So that's why you have this interval. The red curve is above. So what you do is the area will be the antiderivative of the difference of the red curve, which is actually 4 minus x squared. So my bad here. This, as you graph it, you'll find out that this function is above the other quadratic. So when you do the difference, you do the greater function 4 minus x squared, take away, don't forget the brackets, x squared plus 1, expand the bracket, simplified, regroup the like terms, you end up with a simpler quadratics, anti-differentiate the respective term, substitute the lower boundary and the upper boundary. So the upper boundary is on the right, the lower boundary is going to be on the left with a minus, and you simplify your answer. Here, that situation, the red curve is above the blue curve. The general situation is the red curve will intersect the blue curve. So over the whole interval from A to B, you will not have consistently one curve above the other one. As they are intersecting, those intercepts will be used. So you have three intercepts here, C1, C2 and C3. Your whole area you will split into several intervals. The first one will be A to C1, so from A to C1 with the red curve is F. F will be above G, so you will do F minus G. In the next section from C1 to C2, now G is above F, so you will do the difference of G and F. So when you anti-differentiate this section, again it will be an area, and then you will continue with the other two sections. So let's go with an example. Find the area of the region enclosed by the graph of those two functions. It doesn't give you the boundaries, it doesn't give you the graph. So your first task, let's say pause the video, do a sketch, or a sketch of the two curves, then determine the points of intersections. So let's go to the graph. I think it will show the working out as well. So you have your graph here, your straight line and your graph. Notice you have 3 points of intersections, so you need to determine those values. So you make those two functions equal, x squared equals x, regroup on the same side, find the highest common factor, and you use the north factor law to determine the solutions of this equation. So you have x equals -1, 0 and -1. So two integrals to determine the areas from -1 to 0 and 0 to +1. Over those intervals, f is greater than g. In the second interval is the opposite. You write your area for the whole section. Here you regroup, you substitute the functions, you end up with two functions. Notice they are the opposite. So when you anti-differentiate the first one, which is x squared over 4 minus x to the power of 4 over 4 minus x squared minus 2, in the next integral it will be the opposite, x squared minus 2 minus x4 over 4. The boundaries are different, so make sure you just be vigilant at the way you do your working out. Upper boundary, that gives you 0 minus, you substitute -1 into here, that gives you your -1 over 4. Here you have substitute 1, that gives you a quarter, and minus, you substitute 0, that gives you 0. So the left hand side is a quarter, the right hand side is a quarter. Visually you can see the function, there is a symmetry, so the area over here should be the same as that one, and that gives you 1/2 square units. Alright, another example, two functions, in red y equals cos x, in blue y equals sine x, and you can see it intersecting over two values, over here between 0 and pi on 2, and down here between pi and 3 pi on 2. Pause the video. The first thing you should be able to do from circular functions and solving equations is find the exact values where the two functions are intersecting, and if you're up to it, determine the area. Alright, so to determine the intersection, you make the two functions equal, so you get sine of x equals cos of x. You divide by cos of x, that gives you tangent of x equals 1. One value is pi on 4, so you get the first value, which is x equals pi on 4. Don't forget that with tangent you will have another solution in the third quadrant. So if you add pi on 4 plus pi gives you 5 pi on 4, and those values will fit the respective intervals visually. So you need to find the area between from that interval, and notice that the blue curve is above the red curve over this interval, which is your sine. So you do sine of x minus cos of x, and we'll continue with the differentiation. The antiderivative of sine is negative cos of x, minus cos of x is minus sine of x. You substitute the upper boundary and the lower boundary. So that's the upper boundary section, minus square. They use square brackets because you have round brackets. So in those square brackets, you will have the lower part with x equals pi on 4. By doing the working out, you end up with 2 square root of 2 square units. And that's it for today. So see you later.